Hey everyone, and welcome to this explainer. I'm absolutely thrilled to have you here today because we're looking at one of the most incredible realities of human biology. For the longest time, right, people thought of the brain like a computer with fixed hardware. Like once you hit a certain age, your circuits were permanently soldered into place. But that literally couldn't be further from the truth. Your brain, with its roughly 86 billion neurons, is a highly dynamic machine. The fact that it can physically rewire itself on the fly is an absolute marvel. It's constantly changing its structure and function as a direct result of your experiences. So today, we're going to teach this in depth, exploring exactly how that happens, from the tiniest molecules all the way up to massive neural networks. Okay, let's dive right into this. You've probably heard this phrase before. Neurons that fire together, wire together. It's super famous, right? But I want you to understand that this isn't just some catchy self-help mantra or a neat metaphor. This is Hebbian modification. It's a literal physical description of the cellular chemistry happening in your head right this very second as you take in this information. When two connected neurons activate at the exact same time, the connection between them physically strengthens. Here's our roadmap for today. We'll be covering 1. The cellular mechanics of memory. 2. Keeping the brain balanced. 3. Maps, spines, and periods. And 4. Why neuroplasticity matters. Let's kick things off with Section 1, Cellular Mechanics of Memory, focusing on building the synapse. So let's look at how a synapse is actually built and modified. Because the root of all plasticity and memory is the chemical modification of synaptic transmission between your neurons. To really grasp memory, we have to look closely at a process called long-term potentiation, or LTP. This is basically how a neural connection gets a long-lasting upgrade. Think of it like turning up the volume dial on a specific connection. And it happens in a very precise biochemical sequence. First, you get a strong depolarization, meaning the postsynaptic neuron gets highly activated. When this happens at the exact same time the presynaptic neuron fires, it causes these specific channels called NMDA receptors to pop open. This allows a massive, and I mean massive, flood of calcium ions into the cell. This flood is the crucial trigger. It sets off a cascade involving enzymes called kinases, which ultimately leads to step 3. Inserting brand new AMPA receptors right into the postsynaptic membrane. More AMPA receptors mean the synapse is now way more responsive to glutamate in the future. Boom, the connection is officially stronger. Let's look even closer at that trigger, because the mechanism here is absolutely fascinating. Why does it require strong depolarization to open that NMDA receptor in the first place? Well, under normal conditions, that receptor channel is literally plugged up by a magnesium ion. It's a physical block. Think of that magnesium ion like a totally stubborn bouncer at a nightclub, just standing right in the doorway. He isn't moving for just anyone. But when the postsynaptic neuron is strongly depolarized by an intense experience or some really focused learning, that electrical charge acts like the music inside getting incredibly loud. It physically repels and displaces the bouncer, the magnesium ion, kicking it completely out of the channel. That tiny, microscopic shift of a single ion is what unblocks the gate and allows that calcium flood. It's an almost unimaginably small physical movement, but it has massive implications for your ability to form a memory. And you know, this brilliantly illustrates the elegance of our brain chemistry, especially when we compare it to its mirror image, long-term depression, or LTD. If LTP is turning the volume up, LTD is turning the volume down. When synaptic activity coincides with only a weak or modest depolarization, that magnesium plug isn't fully kicked out. Instead, you only get a tiny little trickle of calcium through the NMDA receptors. Now, instead of activating those kinases we talked about, this mere trickle activates a totally different set of enzymes called protein phosphatases. These enzymes pluck phosphate groups off proteins and trigger the removal or internalization of AMPA receptors from the synapse. So the connection weakens. Which brings us to BCM theory. This theory proposes that synapses aren't just one-way streets, they are bidirectionally modifiable. It introduces this really cool concept of a synaptic modification threshold. Basically, there's a tipping point for cellular activity. If the activity is above that threshold, you get LTP and stronger connections. If the activity falls below the threshold, you get LTD and weaker connections. This is exactly why passively reading a textbook, which keeps you below that threshold, doesn't build a strong memory. But actively testing yourself and actually struggling to recall information, that pushes you right over the tipping point. BCM theory is incredibly important here because it provides the crucial bridge between those molecular mechanics we just discussed and the systems-level storage of information across your entire brain. All right, moving into Section 2, keeping the brain balanced, solving the plasticity problem. We really need to talk about solving this plasticity problem. Because think about it. If these synapses just kept strengthening unchecked, every single time you learned something, your brain would become dangerously unstable. Runaway excitation would render your neural networks completely useless. So to solve this, the brain employs some truly mind-bending homeostatic mechanisms. The first one is metaplasticity. This is essentially meta-learning. It's the modification of the rules of plasticity themselves based on the history of cellular activity. Think of this as the brain's internal IT department rewriting its own code to prevent a total system crash. Let's say a neuron has been experiencing a ton of high activity, constantly forming new memories via LTP. To protect itself from overexcitation, the brain dynamically slides that modification threshold we talked about upward. By raising the bar, it makes future LTP much harder to achieve, and makes LTD, the weakening of synapses, easier. The brain is literally constantly rewriting its own rules for learning just to maintain stability. The second stabilizing mechanism is synaptic scaling, and it is a truly profound cell-wide adjustment. Imagine a neuron needs to calm down its average firing rate, but obviously it doesn't want to lose the precious memories it just stored. Memories are essentially just the relative differences in strength between various synapses. So, through synaptic scaling, the neuron globally multiplies or divides all of its synaptic weights by the exact same factor. It scales everything down proportionally. It's incredible when you think about it. The overall excitability of the entire cell drops to a safe level, but the relative differences between the synapses are perfectly preserved. Your memories remain completely intact, while the physical hardware cools off. Let's jump into section 3, maps, spines, and periods. Plasticity in action. Let's zoom out from the chemical level to see how these biological rules literally reshape the physical anatomy of your brain. The chemical changes we've discussed lead directly to structural plasticity. These are literal physical alterations taking place inside your head. When a connection undergoes long-term potentiation, the dendritic spines, which are these tiny little projections that receive input from other neurons, actually physically swell up. They get thicker. They can even bud or sprout completely new contacts just to catch more input from an axon. And here's a wild fact for you. This doesn't take years. This structural swelling and sprouting can happen in a matter of minutes to hours. Conversely, if a connection experiences chronic LTD, those structures literally retract, leading to the complete elimination of that specific synapse. So your brain is like a dense forest that is constantly, rapidly growing new branches and pruning dead ones based entirely on where the electrical energy flows. We actually see this structural pruning most dramatically during developmental plasticity. In early childhood, there are what we call critical periods. During these specific windows of time, the brain is hyper-susceptible to the quality of the sensory environment. The sensory experiences a child has drive massive, experience-dependent synaptic rearrangement. The brain overproduces connections initially, and then completely relies on experience to refine the useful ones and eliminate the rest. This ensures highly precise wiring, kind of like the complex segregation of visual inputs in the visual cortex. And we really must understand the gravity of this. If the early environment lacks stimulation, the physical wiring of the brain is permanently altered. But don't worry, this plasticity doesn't entirely stop in adulthood, especially when it comes to cortical map plasticity. The sensory and motor cortices of your brain contain actual physical maps of your body. But these maps are incredibly dynamic. They adjust based on experience. For instance, if a person tragically loses a finger to amputation, the cortical area in the brain that was previously devoted to receiving sensory input from that finger doesn't just go dark and die. No way. Instead, the brain actively redraws its own sensory real estate. Over time, that completely empty brain area will be taken over and begin to respond to stimulation from the adjacent, still intact fingers. It just rewires itself. We also see this map plasticity applied to positive skill-building behaviors, which is super cool. Look at highly trained string musicians, for example. The ones who use their left hand to rapidly fret notes on a violin show a significant physical expansion in the cortical representation of those specific fingers in their right hemisphere. Their brain literally dedicated more physical tissue to processing the highly complex, rapid inputs demanded by playing their instrument. The actual map expanded to meet the behavioral demand. Finally, let's wrap up with Section 4, Why Neuroplasticity Matters, the functional significance. We've gone incredibly deep into the chemistry, the thresholds, and the anatomical changes today. Now let's summarize the ultimate behavioral purpose behind all of this dense, brilliant biology. First and foremost, neuroplasticity is the physical basis for learning and information storage. Your memories are not some ethereal concepts floating around in a void. They are stored as unique physical patterns of adjusted synaptic weights distributed across massive neural networks. Those tiny volume adjustments we discussed earlier, the precise insertion and removal of AMPA receptors driven by calcium, that is the actual physical manifestation of your memory of your first kiss, or how to ride a bike, or the profound science you're learning in this explainer right now. Furthermore, this incredible biological machinery is our built-in tool for adaptation and healing. Now, it is true that in the central nervous system, adult axons don't regenerate very well over long distances if they're severed. However, neuroplasticity provides a vital, albeit limited, capacity for recovery after a brain or spinal cord injury. By utilizing local synaptic modifications, like sprouting new connections and adjusting synaptic weights, the brain can sometimes literally route around the damage and restore lost function. So the crucial point we should all take away is this. Neuroplasticity is the true engine of behavioral flexibility. In simpler organisms, behaviors are often hard-coded, instinctual, and totally rigid. But because our mammalian circuits can literally be reprogrammed by our daily experiences, we possess a level of adaptability and computing power that is simply unparalleled. We aren't just reacting to our environment is actively collaborating with our biology to continually build a better, more adapted brain. Which leaves us with this final, amazing question to consider. What is your brain wiring right now? Every single habit you form, every skill you practice, every piece of information you choose to focus on is currently flooding your specific synapses with calcium. You are pushing magnesium out of the way, you are inserting AMPA receptors, you are actively expanding your cortical maps. You are not just a passive passenger in a fixed machine. You have immense biological agency over the very architecture of your mind. So, choose your experiences wisely, because your brain is always listening and it is always, always wiring.